time. Okay, so we have got another presentation, very interesting effect of fiber architecture and treatment on dead palm fiber reinforced composite. Is from Dr. Yomna S. Hassan. So please, the online platform is yours. Thank you. From German University in Cairo.
Thank you for your introduction. I will share the screen right now.
Yes, please.
Is it okay now?
Yes, if you could go to full PowerPoint mode, please.
Yes, thank you.
Yes, yeah, it is great.
So,
thank you.
Good afternoon. It's a pleasure to be here today with you. My name is Yomna S. I'm a master's student in Materials Engineering Department at the German University in Cairo. Today, we'll be talking about fibers extracted from the date palm Midrib, and I would discuss the effect of fiber architecture and fiber treatment on the fiber composite performance. So quite often when we talk about date palm, midrib, or fronds, or what so-called ratchets, they are in the form of wooden particles and used as fillers for plastic composites, either for injection molding or for extrusion. So there are actually very few work on the use of textile fibers of the midrib to be long textile fibers used in a formal architecture that could be used in the reinforcement of the polymer composites. And for sure, the textile fiber reinforcement behave completely different than the wooden particle fillers. And that would significantly result in different fiber composite performance. That's why the objective of my research here is to use textile fibers that are extracted from the date palm midrib in different textile architecture and to discuss the effect of this architecture and fiber treatment on the final fiber composites. So for the experimental design, we had two designs of experiments. The first is the design of experiment A. We were studying the effect of three different fiber architecture having equal fiber weight fraction, 50 for the date palm and 50 for the polypropylene matrix. We prepared three samples. The first sample was the non-woven, the second was the commingled, and the third one was the core wrapped. For design of experiment B, we were studying the effect of date palm fiber weight fraction, 60%, 50%, and 40%, and the fiber treatment using Maleic Anhydride. So we prepared two sets of samples. The first set was the untreated, and the other one was the treated. And within each set, we changed the fiber weight fraction of the date palm using 60%, 50%, and 40%. For the sample preparation, we went through two tracks. The first track was for preparing the preforms of the three different fiber architecture. The first one was the non-woven. We prepared this non-woven by mixing equal weight ratios of polypropylene fiber with date palm fiber.
May I just, sorry to interrupt.
Yes, sure.
I'm sorry to interrupt. I think your internet connection is weak. Can you turn off your video to save the bandwidth?
Okay, sure, no problem.
Okay, thank you so much.
Okay, you can hear me better now?
Yes, perfect.
Okay, for the sample preparations, first track is preparing for the preforms. We started by preparing the non-woven architecture. So we mixed equal weight ratios of polypropylene with date palm fiber reinforcement, having equal fiber length of 6 centimeters. Then we used the dry layup method, which resulted in random fiber architecture preform, as we can see it here in its real photo. For the second architecture, we had the commingled unidirectional. We prepared this by mixing equal weight ratios of date palm with polypropylene to form an intimate blend in which the fibers of the date palm and the polypropylene matrix were commingled together and formed a spun yarn. This yarn was then made to form this unidirectional preform. The third architecture was the core wrapped unidirectional. We started by a spun yarn of long date palm fiber midribs that was used as a core. This core, as we can see here in this schematic, was then wrapped by equal weight of polypropylene filament yarn to form the core wrapped spun yarn. This core wrapped spun yarn was made again into a unidirectional preform, as we can see. For the fiber treatment, date palm fibers were treated using Maleic Anhydride coupling agent under a temperature of 55 degrees Celsius for a duration of 2 hours. The Maleic Anhydride was in the form of pellets. Those pellets were crushed into powder and used with a ratio of 10% of the fiber's weight, dissolved in acetone with a ratio of 1:20 weight to volume. The second track for the sample preparation was preparing the composites using the hot pressing machine as shown here. We started by preheating the samples for 1 minute under a pressure of 3 megapascal. Then the samples were hot pressed at 180 degrees Celsius under a pressure of 15 megapascal, and finally followed by a cooling cycle. Afterwards, each sample was cut according to a specific sampling layout. We followed a staggered sampling layout to have the best representation of the samples during the testing. For the testing, the table here below shows the properties that we were testing, the test device used, and the number of the ASTM standard. So we tested for the tensile properties and the flexural properties using the same test device, but we changed the flexural properties using a 3-point bending fixture. As for the drop weight impact properties and the fracture surface analysis, they are still work in progress. Also, regarding the moisture content and water absorption and thickness, we are preparing for those results. For the results and discussion, first, studying the effect of the textile architecture. So here we have the typical stress strain curve and the tensile strength bar chart for the 3 different fiber architecture. As we can see, it's obvious that the non-woven showed the least values in comparison with the commingled and the core wrapped. We can say that because of the non-woven architecture, the fibers are randomly oriented and they are providing reinforcements in all directions. That's why comparing this architecture with the other 2 unidirectional, we can say that in the unidirectional, all the reinforcements are aligned in one direction, which is the loading direction. That's why they had significantly better mechanical performance, not only for the tensile strength, but also the same for the tensile modulus and the breaking elongation. So returning back to the difference between the commingled and the core wrapped in the results, we can see that the core wrapped had better performance than the commingled, and that's because the difference in the fibers from which the yarns are made of in the core wrapped and the commingled. Where in the core wrapped unidirectional, the yarns are made of fibers, long fibers, which are about 1 meter long. But for the commingled, we used spun yarns of shorter fibers that are about 6 centimeters. That's why the load transfer mechanism is much better in the core wrapped than in the commingled. For the bending results, for studying the same effect of the 3 different textile architecture, we can say that the bending strength results showed the same performance or the same pattern of the tensile properties, having the core wrapped as the best results and the non-woven was the least one. Now for studying the effect of the second design of experiment, which is the effect of fiber weight fraction and fiber treatment, we can see here a typical stress strain curve for the different fiber weight fraction, 40, 50, and 60. And we can say that it was found that the 50% was the optimum value for the weight fraction. And this was for the untreated samples. This may be because of the 50% we have enough amount of reinforcements, and at the same time, the amount of polypropylene matrix is enough to ensure sufficient wetting of all the reinforcements and transfer the load. But for decreasing the value of the fiber weight fraction, for example, to 40%, we can say that the number of amount of reinforcement is reduced, so we had lower mechanical performance. And on the other side, increasing the amount of weight fraction, we can say that the 60% we found dry spots in the specimens, and that's because of the polypropylene is not sufficient to ensure complete wetting for all the reinforcements. So for now, for the untreated, for the treated samples, we can say that here, for the treated samples, again, the 50% was the optimum. And comparing the treated samples with the untreated sample, we can say that the treated samples had consistently lower mechanical performance than the untreated samples. This might be because of the fibers could have been exposed to degradation, maybe because of the treatment conditions, it could have been severe. But by examining the fracture behavior of the treated samples, we can say that the treatment had a positive effect, that it enhanced the interfacial bonding and also eliminated any fiber pull out during the fracture. Now for the tensile modulus results, we can say that increasing the fiber weight fraction increased the tensile modulus up to 60%. And this is and here we can see that the stiffening effect is increased. For the treated samples, we can say that the 50% was the optimum. As for the tensile strength results, again, the effect of the treatment here is not significant for the tensile modulus. And this, as I have mentioned, this may be because of the fiber's degradation. For the breaking elongation, even changing the fiber weight fraction did not have a significant effect on the result of the failure strain. And the same was for the untreated samples. Finally, for the bending results for the effect of fiber weight fraction and treatment, we can see here in the typical stress strain curve that by changing the fiber weight fraction, increasing it from 50 to 40, we can say that the bending strength and modulus are increased for the untreated samples. For the treated samples, we can say that increasing the fiber volume fraction did not have a significant effect. And comparing between the treated and the untreated, we can't say that the treatment had a positive effect on the bending strength. And again, we are still preparing for the SEM images to be able to interpret this behavior of not having a positive effect on the mechanical properties for the treatment of the Maleic Anhydride. Finally, to conclude, we can say that the fiber architecture had a significant effect on the performance of the composites. So if we want to introduce date palm fiber composites in structural applications, then the unidirectional would be a very good choice. But if for non-structural applications, it would be a good choice to use the non-woven as it has faster and cheaper production. Regarding the treatment of the date palm fibers, as I have mentioned, that it improved the fracture behavior by eliminating the fiber pull out and enhancing the interfacial bonding. And this, but it has lowered the mechanical performance of the composites, and this is still under investigation. This could be due to the fiber degradation. Regarding the weight fraction, it was found that the 50% showed the optimum results, and this could be a good guiding point for composite designers that are aiming to develop high sustainable date palm fiber composites. And then comparing these results with other leaf fiber composites, we can say that these results are comparable, and that the date palm midrib fibers is considered to be very promising as a novel addition to natural fiber library and also an alternative reinforcement rather than the synthetic ones. Thank you for your attention. I would be happy to answer any of your questions.